Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Ekaterina Stepanova. Ekaterina is a researcher at the Wireless Networks Lab of IEEE RAS, and she is currently working towards her PhD degree at MIT. She received bachelor and master degrees in applied mathematics and physics from Moscow Institute of Physics and Technology in 2017 and 2019 respectively. Today she will tell us about modern power-safe mechanisms in Wi-Fi networks. Ekaterina, the floor is yours.
Thank you for this introduction. Let's start. Okay. Low energy consumption is crucially important for various wireless network technologies. But in modern wireless networks, reducing energy consumption is challenging because of the heterogeneity of the networks, devices, applications that impose different quality of service requirements. A typical example of such heterogeneity could be a home Wi-Fi network that provides connectivity for Ultra HD TV, battery-supplied smartphones, wearable devices such as watches, various smart home sensors, and actuators. In such scenarios, we may have energy consumption tolerant devices that require high bandwidth on one side and low power sensors on the other one. At the same time, there are some devices which transmit heavy traffic from time to time and thus require both low energy consumption and high available throughput, for example, smartphones. Therefore, today I will tell you about modern power-safe methods which may help to reduce the device's energy consumption in difficult scenarios. Before the description of power-safe mechanism, let me describe what the station spends energy on. Today, I will tell you only about the energy consumption of the radio interface. That is, I don't consider the energy consumption for generating or processing frames, etc. It's important fact that the radio spends different energy on transmitting, receiving, listening to frames, and listening to the idle channel. For example, in this presentation, this presentation presents the following power values consumed by the station. In this case, the idle channel is a channel in which there is no transmission or it's not recognized. Okay. According to the basic Wi-Fi power management procedure, a station can operate in active or power-safe modes. When the station operates in a power-safe mode, I will call it a power-safe station. This station can be in DOS or in awake state. In the awake state, the station keeps the radio interface switched on. But in the DOS state, the station turns off its radio. That's it stops both transmitting and receiving frames, as well as channel listening in general, which allows it to significantly decrease energy consumption. If the station is in active mode, it's awake all the time. It should be noted that if the network is heavily loaded, a station can spend a significant amount of energy listening to the transmission of other stations. It happens because the station begins to receive and decode all frames transmitted in the channel until successfully decoding the receiver address or the end of the frame received. Now I will tell you more about the basic power-safe procedure. In networks with an access point, the station must inform the access point about the change in the operating mode. That is both about the transition to the power save mode and the transition to the active mode. To do this, the station must send a frame indicating the desired operating mode and successfully receive an acknowledgement frame on it. Next, if the station is operating in power save mode, the access point buffers frame intended for this station, except for some types of management and control frames. To enforce the power save station about buffered data, the access point in each beacon transmits the team table, which indicate the presence or absence buffered frames for each power save station. Less often, beacons contain the team table, which indicate the presence of broadcast frames for power save stations. The access point sends such broadcast frames immediately after sending the DTIM beacons. Therefore, each power save station should periodically wake up and receive beacons. However, in practice, to save more energy, stations may wake up to receive only the DTIM beacons. If the station understood from the received beacon that there are no buffered packets for it, the station returned to the sleep state immediately after the end of the beacon receipt. Otherwise, using random access, the station sends a special frame base poll to the access point. And in response to the base poll, the access point sends buffered frames to the stations. It should be noted that if I say about DTIM beacons, okay, the station sends base poll after the access point broadcast information for all power save stations. Okay, while using the basic power save procedure may significantly decrease energy consumption, it has several notable drawbacks. For example, power save stations use random access to the channel to send power save, base poll frames. It may lead to collision, retransmission, unnecessary channel listening, and increasing the energy consumption if there are other stations in the network, or if many power save stations start simultaneously requesting buffered frames, which can happen after sending the DTIM beacons. Another disadvantage is the need for the station to wake up periodically to receive beacons. And stations that rarely receive or transmit data spend significant energy to receive beacons. Currently, one of the most promising power save mechanisms is the target wake time. It was first introduced as part of 802.11ah amendment, which describes the operation of IoT devices. But target wake time proved to be so promising that it was adopted by the 802.11ax amendment, which described the operation of new generation of high-efficiency devices. Target wake time is free from both the problem of frequent waking up to listen to beacons and the problem of a significant increase in overhead for sending frames. Target wake time is a power save mechanism that allows the access point to schedule a frame exchange with the station in advance. It enables the station to switch off its radio until the negotiation time and thus not to spend energy on unnecessary listening to the channel between the scheduled transmissions. I will briefly walk you through the target wake time setup process. Target wake time can be established between two stations. However, in this talk, let the power save station be the target wake time requester and the access point be the target wake time responder. So, for target wake time establishment, the access point and the station exchange special frames. In the request, the station indicates the proposed target wake time parameters such as service period duration, its start time, etc., as well as the status, request, suggest, or demand. In response to the request, the access point sends a frame with the same or different target wake time parameters, and with the response status accept, alternate, dictate, or reject. These requests and response are exchanged between stations until an agreement is reached or target wake time is rejected. Interestingly, that for any target wake time capable stations, the access point can send an unsolicited target wake time response, which will initiate the target wake time negotiation process. It's also interesting that in accordance with 822.11ax, after an individual target wake time establishment, the power safe station may stop listening to the regular beacons, but must listen to the team beacons. Now I will tell you a little about the target wake time parameters. Target wake time service period is a time period during which a station is awake to transmit or receive frames. So outside the service period, station may be in a DOS state. Minimum target wake time wake duration is the time interval during which, following each target wake time start time, the requesting star shall be in a wake state even if the station has not transmitted or received frame, or until it has received end of service period frame. Okay. Announced target wake time means that the access point shall not transmit a frame to the requesting star within a service period until it has received a base poll frame from the requesting star. Otherwise, it's unannounced target wake time. The trigger enabled target wake time means that the access point shall schedule trigger frame transmission in each service period and requesting star transmit frame as a response to the trigger frame. Okay. If explicit target wake time is employed, a requesting star receives the next target wake time information in the response from the access point. In the case of implicit target wake time, service periods are scheduled with the frequency that was determined during target wake time establishment. Okay. The use of target wake time implies a predetermined time interval during which the power safe station is guaranteed to be awake. At the same time, the station does not know anything about the target wake time of other stations. Moreover, the service period of different stations may intersect or may be simultaneously assigned. Based on this, it becomes clear that the target wake time setting does not guarantee collision protection for frames transmitted during the service period. However, in 802.11ah networks, one can use the row mechanism for protection, while in 802.11ax networks, one can resolve the channel using RTS CTS or CTS to self frames, or use trigger frame to schedule channel resources. Next. In the ideal case, the access point can schedule non-intersecting service period for transmissions, so that they pass without collisions. But both the sensors and the access point clocks are not ideal, and scheduled transmissions can intersect, which leads to collisions. The Wi-Fi standard allows the clock drift not exceeded 100 bytes per million. So, if we want to guarantee that the station transmits the frame without collisions, we should reserve the channel for this time interval. But if the station wakes up every hour, for example, it may occur in sensors network, then delta is almost 1 second. Reserving the channel for such long time to transmit only one frame significantly decreases the network performance. If the protected interval length is reduced, the sensor transmission can collide with the transmissions outside this interval. To solve this problem, one can reserve the channel for all scheduled sensor transmissions at once. And for it, there is target wake time grouping procedure. Using it, the access point assigned the number to the stations in the group, assigned the target wake time service period to the third station and the time interval between target wake times in the group. Inside the common reserved interval, it's important not to schedule the sensor transmissions too close, because stations transmit their frames using the channel random access, and not too far to avoid unnecessary channel reservation. You can read more about this in this article. Okay. Now, I have to mention the broadcast target wake time. It differs from the individual one and is something in between individual target wake time and the basic power save procedure. The main difference between broadcast target wake time and individual one is that the access point sends all broadcast target wake time parameters in beacons. Immediately, I know that broadcast target wake time is intended both for transmitting individual frames and groupcast, and the groupcast frames can only be transmitted in service period after the team beacons. Okay. The main parameters of the individual target wake time pass to the broadcast target wake time mechanism without noticeable changes. However, new parameters appear, such as persistence or recommendation. Persistence shows the number of subsequent beacons in which this broadcast target wake time will be presented with the current parameters. This is necessary since not all power save stations listen to every beacon. Therefore, it's necessary to inform them about the changes or the end of the broadcast target wake time in advance. The recommendation parameter defines the type of frame exchange that the access point should implement in the service period. For example, recommendation may regulate the presence of or absence of a resource block allocation for random access in trigger frame, require the only broadcast frame transmission in service period, sending team frames, etc. Interestingly, for power save stations, there are several possibilities not to wake up to each service period. One of which is to inform the access point about this by sending a special target wake time info frame, and the other one is to use the wake TBTT. Okay, let's talk about them in more detail and start with the latter. TBTT is target beacon transmission time. Accordingly, this mechanism defines a beacon sequence to listen to which the station shall wake up and be awake during the minimum wake time. Next, target wake time information frames are used to suspend and resume the configured target wake time, both individual and broadcast. It's important to note that target wake time info frames are acknowledged, and accordingly, the commands transmitted in them take effect only after successful ACK received. Now, I will describe an interesting feature of target wake time info frames. It's flexible wake time. If a target wake time info frame with flexible wake time is sent for an existing individual target wake time, the start of the next service period must be changed to the new one. Note that such a frame is not sent for broadcast target wake time due to the fact that it belongs to a group of stations, each of which maintain an independent awake or sleep state, and it can be difficult challenge to inform all stations as a group. Okay. However, the target wake time info frame with flexible wake time may contain a non-existent target wake time ID. In this case, the station must maintain a sleep state from the time the target wake time info frame was sent until the time specified in it. It's important to note that in the described case, the flexible wake time mechanism is independent of the individual or broadcast target wake time. And this important its stations are not required to have configured individual or broadcast target wake time, or even not required to support them. As I said earlier, target wake time may suffer from clock inaccuracy because of long time intervals without carrier sense. The energy consumption caused by unnecessary listening can be reduced by the 802.11ba amendment. Within this amendment, each station has two radios. The primary connectivity radio, which is used to receive and transmit usual data frames, and wake-up radio, which is an additional, very simple radio that consumes thousands of times less energy than the PCR. Wake-up radio is used to transmit management information only from the access point to the stations. Naturally, the concept of the wake-up radio is not brand new, but 802.11b shall make wake-up radio compatible with legacy Wi-Fi. Okay. While the access point transmits a WUR frame, legacy devices that operate in the same band shall understand that the channel is busy. For that, every WUR transmission starts with a legacy Wi-Fi preamble transmitted in 20 MHz band. Legacy devices capture and decode the preamble and consider the channel as physically busy for the whole WUR frame duration. The rest of the WUR frame can be only received by wake-up radio. To reduce power consumption for the receiver, a very simple on-off gain modulation and a narrow band of 4 MHz are used. When PCR is off, the station cannot capture the legacy preamble. So WURSync is used to allow wake-up radio receivers to synchronize to a WUR frame. The structure of WURSync determines which of the two rates, low data rate or high data rate, is used to transmit WUR data. The MAC layer payload in Word data is encoded with a Manchester-based codes as shown on the slide. 802.11b defines 5 types of MAC frames. Wake up and short wake up frames that trigger the station to switch on its PCR. Word beacons that provide timing synchronizations, word discovery frames that contain information about other access point supporting wake-up radio, and vendor-specific frames that are out of the scope of the standard. At the MAC layer, word frames are rather short and contain only these fields, except short wake-up frame. Word frames are transmitted according to EDCA, basic Wi-Fi random access rules. But all word frames are sent without acknowledgement because stations don't have wake-up radio transmitter. Consequently, the retry counter and the contention window of binary exponential backoff are not increased if the transmission fails. To enable wake-up radio, the station shall negotiate its parameter with the access point. After such negotiation, the station can switch off its PCR and switch on its wake-up radio. To notify a station to switch on its PCR, for example, if the access point has buffered that data for the station, the access point sends a word wake-up or short wake-up frame. Switching PCR on takes some time. To notify the access point about waking up, the station may send some frame to the access point. It can be an uplink data frame or a frame which retrieves the buffered data like baseball. The wake-up frame can be as a unicast, broadcast, or multicast. If the wake-up frame is intended not for all stations in the group, then the frame shall contain the frame body field with WUR IDs of all recipients. The short wake-up frame contains only fields on the slide, shown on the slide. This frame is only individual, does not contain a frame body field, and all field which specified. Unicast full wake-up frame and short wake-up frame are interchangeable, and the standard does not regulate exactly which frame need to be used in different situations. However, if the short wake-up frame was not delivered successfully, the standard recommends using full wake-up frame for retransmission. Note, when PCR is off, WUR is on and consumes energy. So its power consumption is much lower than that of PCR. To address this issue, 802.11ba introduces a duty cycle mode. With this mode, the access point and the station agree on strictly periodic time intervals during which wake-up radio shall be switched on. During the remaining time, both radios may be switched off. Duty cycle reduces the time that the wake-up radio is in a wake state, but the price for this is the increased delay for downlink transmission. Next. To maintain connectivity with the access point and to maintain time synchronization when the station's PCR is off, the access point may periodically broadcast WUR beacons. Specifically, WUR beacons contain the partial timestamp of the current clock value. They are sent in a way similar to traditional beacons, however, with a longer period to reduce overhead. An important difference between WUR beacons and usual beacons is the ability to be sent not periodically. If the station uses a duty cycle procedure, it may ask the access point to send special keep alive frames during the WUR duty cycle service period to maintain the connection with the access point. The keep alive frames includes wake up frames and WUR beacons. And if the access point shadows wake up frame transmission in the current duty cycle service period, this frame is treated as a keep alive frame, and additional transmissions are unnecessary. Otherwise, the access point should schedule the transmission of WUR beacon as a keep alive frame. Since a WUR frame is long, it's necessary to group several wake-up frames. The 802.11ba allows transmitting several WUR frames in parallel and different frequencies, one per 20 MHz sub-channel. In this case, the legacy preamble is duplicated in every 20 MHz sub-channel, while the WUR parts are different. When negotiation WUR operation, the access point and the station choose the subchannel in which WUR frames for this station will be transmitted. And some little information about performance evaluation of wake-up radio. Okay, we consider a Wi-Fi 802.11ax network with one access point, 10 usual stations that generate saturated traffic, and 10 sensors, which rarely transmit data frames to the access point. The sensors use target wake time to reduce power consumption, and the access point schedule time for each sensor when it will transmit its uplink frame. At a scheduled time, each sensor wakes up and starts the transmission. Because of clock drifting, the waking time differs from the target time by a random shift distributed normally with the variance sigma squared. We consider 4 methods for organize this transmission. First is target wake time without trigger frames, in which sensor wakes up at a scheduled time and transmits its data with EDCA. Thus, it contains for the channel with saturated stations. Second is target wake time with trigger frames. A sensor wakes up at a scheduled time and waits for a trigger frame. The access point generates a trigger frame for sigma after the scheduled time to guarantee that the sensor does not miss the trigger frame. To send the trigger frame, the access point contains for the channel with usual stations. After receiving the trigger frame, the sensor responds to the access point with a data frame sent without contention. Third is wake-up radio with CTS to self. This method is similar to previous one, but the network operates according to 802.11ba. Instead of trigger frame, the access point transmits a CTS to self frame, which informs the surrounding stations that the channel will be busy during the time interval needed to receive the data from the sensor. After the CTS to self transmission, the access point uses its wake up radio to send the wake up frame to the sensor. When the sensor receives the wake up radio frame, it switches on its PCR and transmit the data frame. And fourth is target wake time with guard interval. In this case, the access point eliminates contention between sensors and the usual stations. It groups sensors and allocates sensors wake up times one by one, with the distance between neighboring times twice longer than successful data frame transmission. The access point forbids other stations to transmit during the time interval that starts for sigma before the first scheduled time and ends with the last sensor transmission. Okay, to evaluate the efficiency of considered methods, we implement them in the NS3 network simulator. This figure shows the dependency of the channel time and energy consumption per one data frame transmission on the variance of the clock drift. The channel time depends on the variance only for target wake time with guard interval, because the guard interval grows with sigma. For other methods, channel time consumption depends on saturated traffic parameters and on the duration of successful sensor exchange. At the same time, the usage of guard interval or wake up radio manifold reduces energy consumption with respect to pure target wake time with or without trigger frame. Wake up radio can provide the lowest energy consumption when clock drift is not too high. For a high clock drift, its performance degrades since the receiver spends energy on channel listening. Although target wake time with guard interval provides low power consumption when wake up radio in case of high sigma. But in practice, reserving the channel for such long time, it's impossible. And in conclusion, I would like to say that if you are interested in target wake time or wake up radio mechanisms, you can study it more detail in this paper. And thank you for your attention. If you have any questions, I will be glad to answer them.
Ekaterina, thank you for your talk. My question is, you describe quite a lot of modifications of target wake time mechanisms.
Yep.
My question is, which of them are mandatory and which of them are optional? Or if you want to implement target wake time, you have to implement all the variety of these mechanisms.
It's interesting question. Okay, as I know, only individual target wake time is not optional. I'm sorry. For 802.11 AX networks, and not networks, but access points. It's how would say all types of target wake time are very different and needs to different scenarios. And I think it's impossible maybe for all station implement all these methods and all parameters. So maybe I don't understand the question, or
No. Your answer correctly. I
yeah,
understand your point of view. Yeah, that only individual activity
only individual. Yeah,
is mandatory. Other
yeah,
optional. Okay, thank you.
yeah. Maybe other questions.
Ekaterina, thank you for your talk. I have one more question. Can Wake Up Radio operate in the channel that's wider than 20 MHz channel?
Could you repeat, please?
Okay. Can Wake Up Radio operate in the channel that wider than 20 MHz channel?
Maybe I don't.
For example, 40 megahertz, 80 megahertz channels.
Yeah. This question about this slide. If we say about Wake Up Radio using in different channel, it's okay. It's a parallel transmission in some channels, and interesting fact that it transmission may be, how would say, punctured. For example, only in the primary channel transmission is required, but all channel transmission may be or may not, and all transmission are similar to the transmission in primary channel. So it's 20 megahertz preamble and 4 megahertz warframe.
Okay, thank you. But so this picture is for one Wake Up Radio. So this 100 and this 40 megahertz transmission is targeted only for one Wake Up Radio, yes, or for several?
Yeah, I think it's quite obvious question to you. So please,
Yep.
can you tell something about 2 stations, 3 stations working together, and they have this wake up ideas of yours? Because the first works in this area for mobile communication was always called collective behavior. But in your case, it's just behavior one station. It's very good. And actually, just first, I would like to say that your English is very good. Now I understood what actually was told. And thank you very much for this clear presentation. So it's just normal question. Could you consider several stations working with the same procedures? How they collide to each other with this wakes up? I'm sorry for interrupting you.
Thank you for your explanation. But okay, because this station agree about working in different subchannels, there is not collisions.
Yes.
It's parallel transmission. Yes, they work simultaneously. Yeah, but it works.
I see. Yeah, it's clear. Yeah, I agree with you. Thank you very much.
Thank you.
Okay, thank you for your answer to you answered one of my questions. Thank you.
Ekaterina, I have one more question. So in the beginning of your talk, you clearly stated that you only consider the energy spent for transmission, and you do not consider the energy spent on signal processing, etc.
Yep.
But do you have any ideas on how the energy spent on transmission compares to processing? Is it higher? Is it lower?
Oh, it depends. It depends on devices, on networks, on frames. For example, for processing or for generating ARC frame, we in this situation we not have a lot of energy, but maybe for generation some in other words, sometimes we need to time to generate frames, and it's time so big, and we may not answer quickly. So in this situation, I think the energy may be higher for processing, or for generating. It's it's interesting question, but it depends. And when we say about amount of frames, I think generation may need a lot of energy, maybe higher energy than on transmission, maybe. In other words, it depends on number of transmissions, numbers of retransmissions, and etc.
Okay, I see. Thank you very much.
Thank you for the question.
Ekaterina, maybe you can comment on the maybe some plans which are for further development of TWT or something. Is it already known which directions are considered for further improving of TWT?
I'm sorry, but I don't know what I may say on this question, because for me, I studied only target wake time grouping procedure, and target wake time individual, with or without trigger frames, but only individual. But there is a lot of different parameters and new interesting features which appear recently in the IEEE 2.11 AX amendment. I think it may be very interesting fields for study, but...
Okay, thank you. I understand. Just your research is about .11ax, and maybe in .11be something new will be proposed, but it's out of scope of today seminar.
If I may intervene, I'm Dmitry Bankov, Katya's co-author in the papers about TWT. And well, I can say that currently TWT is being developed further in the newest Wi-Fi amendment of IEEE 2.11be. And one of the ways to develop TWT is to introduce restricted TWT, which will make devices, well, currently, if a station has a TWT service period, other stations still are allowed to transmit during this period. So it is up to the access point to protect the transmissions by the TWT station. But in 802.11be, it is proposed to create restricted TWT so that the devices by the standard will be forbidden to transmit during these restricted service periods. So it will be a kind of a way to protect the transmissions from interference from other devices.
Thank you, Dmitry. It's interesting.
So I guess that's all questions. I would like to thank all the participants for participation in the seminar, and especially I would like to thank our presenter Ekaterina. The next seminar will be held next week at the same time, and it will be devoted to the restricted access window mechanism in .11ah network. See you next week. Thank you.
Thank you.